Hi everyone, thank you for being here today watching this presentation. This work is entitled Design Aeroelastic Analysis of Truss-based Modular Wing Structures. My name is Igor Luiz Silva. I'm from Federal University of Uberlândia in Brazil. This presentation will cover the following contents. We have introduction, formulation, wing design and optimizations, and summary and conclusion. All right. So, as you may have noticed, in the last years, with a global debate increasingly focused on environmental impacts and other climate changes, engineers and researchers have been dedicating efforts to develop increasingly efficient aircraft, that is, aircraft that are increasingly lighter and that consume less fossil fuels. So, we currently have a lot of attempts to create new approaches to our aircraft design that are lighter and easier to manufacture. In this context, we bring the idea of truss-based modular structures, which is basically the replacement of conventional structures such as spars and ribs by modular structures, specifically the truss. From that, we can say that the main benefits of modular structures are larger product variety, simplification of construction, easy of manufacturing, easy of assemble, easy of repair, easy of Okay, I won't spend too much time here since you have more details in the paper, but we use the doublet lattice for the aerodynamic modeling, the library for Python developed by Saulo Castro in the structural modeling called PyFE3D, and the PK method for the elastic modeling. You can check for more details in the paper. So for the wing design optimization, we have here the core of this work, the wing design approach. The idea, once again, is to replace the conventional structures of a wing, such as a spar and ribs, by modular structures, specifically the truss ones. So, since there are no ribs that form the airfoil, some control points are used at each cross-section. These control points are defined by means of a spline in order to guarantee the selected aerodynamic profile. As you can see, this figure shows the spline in the corresponding control points for a profile NACA 2412 with 8 and 20 points. It's worth mentioning that those control points are going to be the nodes of the finite element model and the connection nodes of all elements. Right, now we need to connect those control points and create a spatial mesh along the structure. As you can imagine, the spatial arrangement of such structures is a big deal. Therefore, in this work, we use the Delaunay tessellation to connect the cross-sections nodes and so create the maximum truss elements without physically crossing them. On the left, we have an example of a mesh for 8-point spline we generated 345 truss elements, while on the right, the 20-point spline generated 937 truss elements. To perform our analysis, we needed a wing box model. We select the FlexOps wing since it has been studied by other authors in terms of structural design and aerodynamicity. And here you can see the main geometries and dimensions of as you may have noticed, the definition of the number of cross-sections and the number of control points in each cross-section directly affects the number of modular structures created by the Delaunay spatial tessellation. Since the wing design proposed in this work is to generate the lightest possible wing using modular structures, it is necessary to think in terms of optimization. So we seek for the best combination of design variables that minimize the structural weight of the wing and maximizes the flutter speed, taking into consideration structural and elastic constraints. So the first optimization we have as design variables the number of control points, the number of cross-sections, and the diameter of all elements of modular structures, which are considered here as solid truss bars. More details regarding the parameters that we use for the optimization you can see later in the page. Here we have the first Pareto font. It shows that to maximize the flutter speed targeting a better elastic behavior, there is an impact on the structural weight of the wing. Also, it is possible to have a lighter wing, but the flutter speed is compromised. This trade-off is important in aircraft design, since the choice of design variables defines the structural behavior and affects the overall aircraft weight. Regarding the design variables, the optimizer found different combinations that delivered that result, selecting 4 points from the Pareto we have four different options for the wing design. P1 is the case where the wing has the lowest weight and worst flutter speed in that range. At the other end, P4 is the case where the aircraft has the highest weight of the best flutter speed in that range. The other point between P1 and P4 have different combinations of the design variables. The details of the wing optimization of the 4 points selected are displayed in this table. In optimization 1, we can see that it's not very efficient to consider all the modular structures as solid bars. Therefore, at this point, the objective is optimize all the modular elements individually. In other words, the optimization will try to eliminate some elements and will check how the resultant weight and elastic behavior are. The optimizer will design the wing eliminating or not the lattice elements. In addition, The outer diameter and tubular thickness of each individual element will be optimized. As you can imagine, to do so, it is necessary to know the number of lattice elements in the structure in order to optimize them. And to know this number, it is necessary to previously define the number of control points in each cross-section and the number of cross-sections along the wingspan. Only then it's possible to obtain the number of optimization variables. So it is important to first define the values of number of control points and number of cross-sections. Since both parameters can vary in a range of possibilities, the approach here is to select some pairs of those values in order to investigate how the optimization evolves with changing parameters. Thus, the multi-objective optimization problem 2 is summarized as follows. So for this work, three pairs of values of number of control points and number of cross-sections were chosen. All three pairs of configurations generate different numbers of elements and design variables, which are summarized in this table. The three Paretos show different wing designs for the problem previously defined. It is worth mentioning that there are few points in the Paretos. This happens because the floater solution PK method using this optimization considers a speed increase of 1 meters per second. Selecting only the parameter in blue, since it brings the greatest cost benefits in terms of structural weight and aeroelastic behavior, the vertically expanded Pareto. So it is possible to verify only a small change in weight along the y-axis, while there is a considerable gain in flutter speed along the x-axis. Each point of the Pareto represents a different combination of design variables, which in this case, it means a different combination of outer diameter and tubular thickness. So selecting 2 points from this Pareto, that is P5 and P6, we have. Here you can see the original meshes, the elements to be deleted in red, and the remaining mesh. As you may notice, the number of original mesh elements on both wings, points P5 and P6, were equal. However, during the optimization, the algorithm defined different thicknesses and diameters for the elements, in addition to eliminating different elements that were identified as unnecessary. These figures illustrate the distribution of outer diameter and thicknesses per element for both points P5 and P6. The figure shows the distribution of outside diameters, where the elements in blue correspond to the diameter of 10 millimeters, red is 15 millimeters, and orange is 20 millimeters. We also have distribution of thicknesses, where the elements in blue, red, and orange correspond to thicknesses of 2, 4, and 6 millimeters, respectively. More details and comments you can see in the full text version. So that this work brings to light a new wing structural design methodology using modular structures and meshing using Delaunay triangulation. Modular structures can become a great strategy in the design of aeronautical structures, mainly in wings. Modular structures would be interesting to lighten the structural weight of the wing and at the same time meet the structural and elastic requirements. Modular structures bring easy of fabrication as it is possible to choose some specific tube diameters and just cut the required tube sizes, and in smaller aircraft such as radio-controlled and UAVs, 3D printing can become an interesting alternative in the manufacture of such structures. Thank you all for watching.